Hi there, and welcome back. In this video, we'll be discussing section 5.2 further, and in this particular video, properties of the expectation and covariance operators. So last time we defined these things, expectation and covariance, when we had two random variables, capital X and Y, and we'll be discussing some of their properties. So to begin with, let capital X and capital Y be continuous random variables. It follows that all the results in this video will follow as well, given that these are discrete random variables. But to make life simple, we'll just assume that they're continuous. So let capital X and capital Y be continuous random variables with joint PDF f of xy. Then for any function h of xy, we saw last time that the definition of the new random variable h of xy, which last time we denoted by z, but the expectation of this function of random variables, which is also a random variable, is given as follows. So we can compute things such as expectation value of x, expectation value of y, so on and so forth, expectation of x plus y, any function that we can think of using capital X and capital Y. So the first thing that we should know, so expectation was an operator that we were first introduced to in chapter 4. Or chapter 3, in fact. And there we saw that expectation was a linear operator. And it turns out that under this new definition, or this extended definition, I should say, expectation is still a linear operator. So that's our first proposition here, is that the expectation operator is in fact a linear operator. What does this mean? This means the following. The expectation of a linear combination of the random variables capital X and capital Y is given as follows. So to prove this, this is also true again in the discrete case, but I will only be providing a proof in the continuous case. So by definition, using our definition of expectation, the inside function here is ax plus by. Therefore, it's a times little x plus b times little y multiplied by our joint PDF. So, since Calculus 3 was not a prereq for this course, double integrals you might not be as familiar with some of the properties of double integrals. So it should be emphasized that when we're doing double integrals, we can really think of this as applying integration twice. And we know plenty of properties of integration from Calculus 2, so we're going to assume that. So this is then equal to the integral from negative infinity to infinity. This inside bracketed piece is an integral, and the integral, this definite integral from negative infinity to infinity, is linear. So using the linearity of the inside integral, we have that this inside bracketed piece can be expressed as follows. So it looks like the following. Now, applying the outside integral to this linear combination, we can now use the linearity of the outside integral to give us the following. So kind of squeezed in there at the end. So what is this all equal to? So the brackets here again were just for emphasis to help us understand that we're integrating. These two integrals can be thought of as broken up like so. So the one integral is inside the other. We could remove them though. This is just equal to a, by definition, our inside function here is just x. So this is a expectation of x. And similarly, this is b, expectation value of y. So it should be emphasized that this linearity is not a surprising result because simple integration, just like integration, is also a linear operator. So since expectation ultimately is defined by the integral operator, it's natural that the expectation operator is also a linear operator. So the linearity of the expectation operator for several random variables will be useful in the following results. So last time for a definition we defined the following. The covariance operator, which is an operator that takes in two random variables and gives us back a number. And it is defined as follows. It is the expectation of the following product. So last time we looked a little bit at what covariance was measuring. It seemed to be measuring the linear relationship between x and y, capital X and capital Y. In this video, though, we'd like to look at the properties of covariance, some of its algebraic properties. So it will be helpful, instead of representing these as mu sub x and mu sub y, we'd like to be more explicit. Mu sub x is just expectation of x. And mu sub y is just expectation value of y, like so. Well, the covariance operator, like the expectation operator, can be extended to beyond random variables, just capital X and capital Y. In fact, we can define the covariance operator for any random variables defined by capital X and capital Y. So, to be explicit, let capital U be the random variable defined by h of x comma y. So again, h is just some function of two variables, and if we define capital U in such a way, this defines a new random variable. And similarly, let's define capital V to be another random variable defined by the function g of capital X and capital Y. So h and g are just scalar functions of two arguments. So for given these two functions, we have two new random variables. Then we can define the covariance of u comma v to be the following. So with this said, we now have the following proposition. So for convenience, we will define the random variable capital Z to be some new random variable defined by as a function of the old random variables. Then the following properties hold. So covariance is a symmetric operator. So in other words, we can swap the arguments and they're the same thing. So this is symmetric. Property 2 says that covariance is linear in the first argument, so in the first term. In other words, linear combinations in the first term, we can distribute the covariance operator over that first term and factor out constants. Notice that the z stays the same. And so this is for any such z. So for any random variable z that we define as a function of the old random variables, capital X and capital Y, this relationship holds. So covariance, like expectation, is linear, but only in the first component here, by property 2. Property 3, which puts properties 1 and 2 together, we get as a quick consequence that the covariance operator is also linear in its second component. Therefore, we say the covariance operator, by properties 2 and 3, is a bilinear operator. So it's linear in each of its components. So it has 2 components or 2 arguments. It's linear in each of these arguments. And then finally, number 4, it should be noted that in the particular case where capital U and capital V are just equal to capital X, this reduces to our variance of X. So to prove these results, we'll have the following. For the first property, this is just a product of random variables. Well, multiplication is commutative, so therefore it must follow that this is true. And by definition, that is the covariance of y comma x. So therefore, the covariance operator is symmetric. To show linearity in the first argument, we have to use the definition. So this is the, by definition, the expectation which looks like the following. And so we saw from the previous definition of covariance that this first argument is just a new random variable. So the covariance of this pair of random variables is given as follows. That new random variable, subtract the expectation of that random variable, multiplied by z minus expectation of z. The idea is to use linearity of the expectation operator to get our result. So to begin with, for the inside expectation from the last theorem, we can use the fact that expectation is linear. So this is then minus the quantity looks like so. Okay, so a lot of parentheses. The first term here, so the big outer parenthesis, let's try to draw bigger parentheses here to emphasize. So that first term in the bigger parentheses, we're going to group the terms together. So this is going to be ax subtract a expectation of x, resulting in the following. That is these first two terms. Ax subtract a expectation of x is the following. A times x minus expectation of x. Similarly, by subtract b times expectation of y is b times, just like so. So that is the first parenthesis here. Nothing has changed with the second term. We'll now distribute the second term to each one of these individual terms, resulting in so here we've distributed the right term to the first term in the left. So the left term here, the big parentheses, is a sum of two terms. We're distributing the right term to the first of these terms, giving us the following. Similarly, just like so. We will now finally use the linearity of the expectation operator on the outside to distribute to each one of these terms, resulting in the following. So we can distribute the expectation to the first term, pulling out the constant a, resulting in resulting in the following. So by definition of covariance, this is the covariance, this first term expectation of this product is the covariance of x and y. In the second term, x and z. Sorry about that. It's the covariance of x and z plus b times the covariance of y and z, which proves the result. In other words, covariance is a linear operator over the first term. So it's linear in the first component there. Using 1 and 2, we get property 3. Property 3 being which I will just restate here. The proof is left to the viewer. In other words, the covariance operator is also linear in the second component. And so this will follow simply from the fact by symmetry. Since covariance is symmetric, you can change the place of z in the first component and then use property 2 to get the following. So 3 follows immediately from properties 1 and 2. The last property of interest is the covariance of x and x. So in the particular case where u is equal to x and v is equal to x, it follows that the covariance of x and x, by definition, is the expectation of the following product but this expression, recall, this is how we defined the variance of x back in chapter 3. So this is the end of the proof. And these are 4 important properties that we'll use of covariance. So in other words, we saw last time that variance itself was not a linear operator, but using the fact that covariance is a bilinear operator, and the covariance of x comma x is equal to the variance of x, we can derive all the same results of variance of x and further results by using the covariance operator. The next video we'll talk about more properties of the covariance operator together with the correlation operator.